Hi there, I'm Adam from CatBorg Studio. Welcome in third episode of Let's Make Zombie Survival Game. In this episode we'll focus on camera controller. Let's start our epic game development journey.
As we can see, our player moving really smooth inside buildings, although he is able to go off from the screen. In order to fix it, we could simply attach camera to player game object, but overall result will be really stiff and lazy. So, we'll write some camera controller with few cool features. Let's start by going to scripts folder and creating new script. Change name for camera controller and open it. Now, time for a few quick fixes. Let's remove all of not needed lines and elements. Due to the fact that our player is moving via physics, we'll use fixed update for moving camera after him. Now, let's add few comments in order to frame our work. Each frame of fixed update will start by calculating desired position. Then, we will smooth it. And finally, smoothed position will be applied to camera transform. Now, let's declare few variables. We will start by serialized field transform m underscore target to follow. Next, let's declare serialized field float m underscore smooth speed. We will also need serialized field vector3 m underscore offset in order to change camera position. In order to prevent garbage collection on each frame, we will declare two more vector trees. First, m underscore desired position, and second, m underscore smoothed position. Now, let's jump to fixed update void. In order to calculate desired position, we need to grab target to follow position and add offset to it. Then, let's set transform position to calculated desired position. Before we enter play mode, let's assign our camera controller script to main camera game object. Let's assign target to follow reference. Now hit play and continue. As we can see, camera following our player game object, although currently is inside it. To fix it, we need to offset its Y position. Perfect. Now, let's add one extra line to our code. We'll calculate smooth position. In order to make it happen, we'll use vector3.lerp. This function will provide us interpolated position between 2 points according to provided float value. If we feed it with 0 as float value, vector3lerp will return first vector3. If we feed it with 1, we'll return second vector3. Let's finish our code now. First input value, type of vector3, will be current transform position. Second input value, type of vector3, will be position we want to reach. Finally, third input value, type of float, will be smooth speed. Although through perspective of single step, this vector tree lerp don't look like anything fancy, remember that we will conduct many fixed updates each second. And each iteration will get us closer to desired position by a smaller step. Before we enter play mode, we need to rewrite last line, so transform position will be set to smooth position. Let's enter play mode. As we can see, with smooth speed set to 0, our camera remains static. Let's take a moment to play with different values. Remember that changes made during play mode will not be stored. As you can see, camera following player game object correctly, although we could add one more cool feature to it. In second part of this video, we will set up camera bounce in order to limit camera movement to floor of our building. Now, let's add serialized field mesh renderer m_floor. So we will be able to assign and use our mesh renderer building floor to set up camera boundaries. In order to store and use these boundaries, we'll need some variable type of bounce. Let's name it mCameraBounce. Camera bounce need to be established before first update iteration. Perfect place for it will be start void, which is called only one time. Let's jump inside start void. Begin with declaring temporary variable type of bounce. Name it _floor bounce and assign its value to our mesh renderer mFloor.bounce. Another temporary variable will be reference to our main camera. Let's declare a variable type of camera, name it _main camera, and set its value to camera.main. Now we'll need to grab camera height and width. Let's declare float _height and assigned main camera.orthographic size to it. In order to get width, let's declare float _width and set it to height multiplied by main camera.aspect. So, to make this bound things working, we'll need 4 limiting float values. We'll start with how far camera could go to left and right. We'll declare 2 float values, _min x and _max x. Let's declare float _min x and set its value to floorBounce.min.x increased by width. Now it's time for underscore max x value. Set it to 2 multiplied by floor bounce dot extends dot x decreased by width. Time for next two limits. Our camera exists in 3D space, pointing straight down on player. So in order to move it from bottom to top of screen, we need to change it Z position. Let's declare float underscore min Z and set its value to floor bounce dot min dot Z increased by height. Finally, declare and set underscore max Z value to 2 multiplied by floor bounce dot extends dot Z decreased by height. Now, time for declaring initial value of m underscore camera bounce. Set it to new bounce. We are ready to establish the min and max value of bounce box. Write m underscore camera bounce dot set min max. Set min max need to be fed with two vectors tree. Let's create new vector tree with prepared min values. We'll input 0 in Y position. Second vector tree will consist of max values. Create new vector tree and input max x, 0, max z. Great, we finish worst part. Now, let's add some vector tree which will grab some position and apply bounce limit to it. We will call it limit camera to bounce. It will require vector tree as input. Let's name this input vector tree underscore desired position. So, when this vector tree will be fed with underscore desired position, it will return some new vector tree. And this new vector tree will have its x and z values limited to our prepared bounce. In order to achieve it, we'll use math.clamp, which is nothing more than looking nice and fancy if call. So, how this math.clamp works? It's requiring three input values. First is current value. Second, minimal allowed value. And third, maximal allowed value. Nothing hard, but very useful. So, let's focus on x value of our new vector tree. Let's write math.clamp and feed it with underscore desired position dot x, then with m underscore camera bounce dot min dot x and m underscore camera bounce dot max dot x. For the y value of our return vector tree, let's write underscore desired position dot y, so it will stay unchanged. Finally, time for z value of our new vector tree. Again, let's write math.clamp and feed it with underscore desired position dot z, then with m underscore camera bounce dot min dot z an m underscore camera bounce dot max dot z. Great. Now our m underscore desired position could be limited to prepared camera bounce. Let's write m underscore desired position equal limit camera to bounce and feed it with m desired position. Before enter play mode, remember to assign m underscore floor mesh renderer reference to our camera controller script. Seems working. Let's go up and examine top boundary. Looking fine, but when going to right limit, we had this weird camera jump. That is because camera size is wider than floor. In order to fix it, let's change camera orthographic size. Decrease it to something like 4. Enter play mode and check out how it's working. That's great. Before we finish, let's add few more details to our script. Let's start by serialized field boolean m underscore limit camera. This will allow us for turning on and off this new feature from inspector level. Now, simply add value checking of m underscore limit camera before overwriting of m underscore desired position with boundaries. If value is true, m underscore desired position will be limited to respect camera boundaries. Enter play mode and check out our new feature. Working fine, so let's add some more small details. Get back to our script and add header attribute in order to separate boundaries section in script inspector tab. Finally, let's check out one more attribute. As our m underscore smooth speed works only between 0 and 1, let's add range attribute to set it. Now we are able to change m underscore smooth speed according to its designated values.
That's all in this episode. Let me know how do you like this content in the comments below, and see you in the next one.